Hi, I'm Anna, and today I'm going to explain the start of the journey, the first part that will be the green ramp. So at this point, the ball is at its highest point. So it means that it has the maximum gravitational potential energy because it hasn't started moving yet. So the formula that we would use to calculate it will be this one. That is potential energy equal mass times gravity times height. If we assume that the first card weighs 60 grams, that in kilograms will be 0.060 kilograms, and then the green ramp is approximately 1.2 meters height, then the formula will be this one, that is potential energy equals 0.060 kilograms, that is the weight of the car, times 9.8, that is the gravity, times 1.2 meters, that is the height in meters of the green ramp, equals to 0.7056 joules. Okay, well, when we release it, this potential energy is progressively converted into kinetic energy, which is the energy of the motion. But we also lose some of that energy due to friction with the ramp. Well, we estimate maybe the 15% of the total that is lost, which is quite realistic in real physics system. So this ramp begins the journey of the energy, starting with a potential energy and then going with kinetic energy, and it have a loss due to friction.
Hi guys, I'm Isa Franco and I'm going to explain the next part of the ramp, which is the orange one. So first we have to know that the ramp is slightly lower at 1.0 meters. So we have to repeat one principle. This principle will be like EP, that is equal to m times g times h, which will be mass, gravity, and height. So we replace those values and we will have 0.060 times 9.8, which is the standard value of gravity, times 1.0. And then we have the result of 0.588 joules, which is like the result of this principle. And then we have friction, which is at 15% the useful kinetic energy, and is maybe reduced to EC, that is equal to an 85% of 0.588, which is rounded out to 5,998 joules, which is speed of 4.08 meters per second. So it is important to understand that although the ball continues to descend, it does not accelerate as much as it will under ideal conditions. This explains a lot of the non-conservative system of this model that we can observe later. Also, friction is a force that always opposes movement, and it's translated into transference of parts of energy into some heat and sound. This is a great demonstration of the law of conservation energy. Energy is not lost, but it's transformed. So thank you guys. We're going next.
Hi teacher, so I will explain the purple and blue ramps. So the purple ramp has a weight of 8.8 meters with a potential energy of 0.60 plus 9.8 plus 8.8, which is a result of 0.4704 joules. After the friction, we see that the speed is 3.65 meters per second. Then we have the ramp that goes down, that has a weight of 0.6 meters, which potential energy is 0.016 plus 9.8 plus 0.6, which give a result of 29.99 joules with a speed of 3.16 meters per second. At this point, we already know that the speed of the balls depends directly of the kinetic energy, but it doesn't increase as much in the theory, precisely because the friction accumulated in this effect. So we can say that the ramps shows that an energy continues to be transformed, but it's part of lost in mechanical terms.
Okay, hi everyone, my name is Lilian and I have the part of the red ramp that it's a curved line. Here we have to know that the height is about 0.5 meters. What means that if I want to calculate the potential energy, I have to multiply 0.060 times 9.8, that is the gravity, times 0.5, that is the height. That would give us a 0.294, that are the joules. And now, if I want to calculate the kinetic energy after friction, I have to get the 85% of this previous value, I mean of 0.294, what would give us a 0.2499 joules. And that if we calculate this, it would give us the speed, that is 2.89 meters per second. Something interesting about this thing is that the ramp is curved in its shape. So what it means that at the same time that with the gravity it increases its velocity, with the friction it decreases its velocity, because if I have a ramp that is at this, like in this point, and if there's an object falling off, if I have a gravity, it will fall down faster because the gravity attracts it to the center of the earth. But with the friction, it reduces a bit its velocity. So I think that it reflects the perfect balance and the combined effect of gravity and friction acting at the same time.
So finally, the actual kinetic energy will be calculated with the formula kinetic energy equal to 85% of 0.2058. That is equal to 0.1749 joules. With that energy, like the ball travels at a speed of roughly 2.41 meters per second. We make the calculations, which is still pretty good, although it has already lost quite a bit of energy since the beginning of the circuit. It still has enough to continue on its way and activate the cups. This shows us that although we start with more than 0.7 joules at the beginning of the Rube Goldberg, at this point we are already down to less than 0.18 joules. In other words, friction does affect motion and a lot. So finally, the actual kinetic energy will be calculated with the formula kinetic energy equal to 85% of 0.2058. That is equal to 0.1749 joules. With that energy, like the ball travels at a speed of roughly 2.41 meters per second. We make the calculations, which is still pretty good, although it has already lost quite a bit of energy since the beginning of the circuit. It still has enough to continue on its way and activate the cups. This shows us that although we start with more than 0.7 joules at the beginning of the Rube Goldberg, at this point we are already down to less than 0.18 joules. In other words, friction does affect motion and a lot.
Well, so my part is cup systems and final section, green, orange, red, and purple. I'm Santiago and display the final system of ramps and cups, which includes several small sections and different colors. Here are the ball details from a height of 0.2 meters. The potential energy, it's going to be 0.060 multiplied by 90, but there is the formula, that's equal to 176 joules with 50% loss. The kinetic energy is going to be 80% of 0.1176. That's equal to 0.999 joules. The speed is going to be 1.83. In this final section, our turn, the ball is still moving. Almost of the initial energy has been converted into different forces: heat, sound, and some energy is displaced in these cups. The section shows how the system is designed to conserve mechanical energy as long as possible, but the progress and inevitably transformation of energy is visible. In a total of initial 0.7056 joules, also like 70,056 joules, the ball ends up with 0.0999 joules of useful energy, indicated that approximately 0.66057 joules were lost due to the friction with the friction, which consists in the physical system which continue contact. In summary, this project demonstrates conservation and transformation of energy, effects of friction, acceleration motion along an inclined plane, real-life application, potential and kinetic energy formulas. The model is not visual, but to the real-life physics, that is a very, very interesting point, so thank you.